Hello everybody, I would like to start a series of lecture about MIPS instruction set. These lectures will help you understand the underlying working of a MIPS instructions, and this will help us understand more the hardware that will be coming in the next few lectures. This is not a comprehensive list of all instruction set, but just a few to help us going on with the hardware. So before starting, we'll be discussing a 32-bit MIPS processor. So usually a processor will have some inputs and will process them to generate some outputs. So what do we mean by processing? Usually what processing means is actually carrying on or executing instructions. What are instructions? Instructions are just a series of commands. They are a list of commands that will help us execute a specific task, such as add, subtract, average. As we know, the underlying processes of any processor usually deals with arithmetic and logical operations, and here where the commands help us to do this. And commands, or instructions in this case, need variables. So our variables should be placed inside the processor in a component. So if we just want to list a small overview of what's inside this processor, we can imagine that it has a program memory, where all the instructions are placed. Of course, this is a 32-bit processor, and the size of the instructions is 32 bits. Now, from this program memory, an instruction is fetched. This instruction will be our command will be like adding or subtracting or any other operation that we desire. However, as we said, the commands needs variables. So from this instruction, we need a place to place our variables, and this place is called the register file. So this register file is just a big memory, or it's not that big, it's a small memory. We'll see about the size later, and it has some registers. This is where our variables will lie for the x equal 5, y equal 6, and we can manipulate those variables, change their values, do some operations. Of course, since this is a memory, we need some addresses to tell us where our data is found. So, of course, in MIPS processor, we have two inputs for fetching two variables from our register file. And since this is a 32-bit processor, this means the data is 32 bits. This means the output of the registers, which has our variables, is 32 bits. Now, of course, we need to add, subtract, and do all these logical operations, so we need an ALU. In this ALU, we can do the addition, subtraction, all this operation, and then we have the data. Of course, the ALU takes two inputs, each of 32 bits, and generates an output of 32 bits. This value, of course, should be saved. So where we save our variables is in the register file. So this line will go like this inside the register file. So these two addresses will, let's press address 1, address 2, will get us source 1, source 2, and of course I want an address to save my data. So of course I need the third address, which is called address 3, which will save the 32-bit data. Of course, the address and the size of the address is irrespective of the size of the data bus, because this address will help us compute the number of locations or the size of the memory. So to continue with this discussion, I'm going to explain more about the register file. So let's go into deeper of how the register file is organized inside the MIPS processor. So I'm going to draw it again, but this time I'm going to label my addresses. So I'm going to call this RS, this RT, and this is RD. And of course I have the data, which is 32 bits. And I have two outputs. This is also 32 bits. And this is what's inside RS, or the better way to explain it is the data pointed by RS and the data pointed by RT. So these addresses are 5 bits in length. What does this mean? So addresses in the register file are 5 bits. This implies we have 2 power 5 is equal to 32 locations. Of course, each location has a 32-bit variable. So let's say I want what's inside this location, which is, let's say, 10. So I need to place 10 and let's say 11. So I need to give the address of 10 and give the address of 11 to have them here. Of course, RS will give me what's the content point by RS, and RT will have its value here. Now, so these registers have a way of identifying them. So one way to identify them is just by adding $0 or $1, $2, and so forth till $31. So this means $0 means content at address 0, and also $31 means content at address 31. So a way to identify these registers is by just giving the number, the location with the $. Another one is by naming them. So the MIPS reference sheet indicates there are a few ways or few registers that are used. So the first one is we're going to talk about $0. So inside $0 is just the value 0. So it's 0x1, 2, 3, 4. So it's of course 32 bits, and what's inside $0 is always 0. It's hardwired to 0, which means that you cannot change the value, you cannot manipulate it. We have also some handy naming registers for us, as $0 to $7. They are found in locations 16, so location 16 to 23. We also have $T0 to $T7. These are also 8 registers we can use, and they are found in location 8 till location 15. And of course we have T8 and T9, 2 more registers which are found in location 24 and 25. So the difference between S and T is that S holds its value during a procedure call. T are just can be thought of temporary variables or of values that can be changed frequently, of little importance to us. So we just focus on S when we need values to sustain a call or for a procedure, while the dollar T's are just variables that can change. So now using these registers is very easy. We're going to start with instructions. The first instruction for our MIPS processor, and this instruction is called add. So add takes three operands: $RD, $RS, $RT. So here we use just the naming of the addresses of our register file. We add the $sign to indicate that it's a register. Okay, so what this operation does is that it places the addition of RS and RT into RD. So we're actually fetching the values inside the register file and then adding them together. For example, let's say I have this register file and I want to place, let's say this is in location 8, 9 and 10. Of course the register file goes further to location 31. So let's say I have value 10, 12 and 13. So we can identify that 8, 9, 10 are the locations of these values. We'll worry later about how these values came inside the register file. We're just focusing on the add operation. So here we can say add. Let's say we want to add the value inside 9 and 10 and place it in 8. So what we do is add $8, $9 and then $10. So what happens is that $8, what's inside of it, or in this case we can say just 8 since it's the address, is equal 25. So this will go and we'll have 25 inside of it. We can also use our named register, since we know that 8, 9 and 10 are just T0, T1, T2. So this is $T0, $T1 and $T2. We can say this is add $T0, $T1, $T2. So we're adding those two values and placing them into T0. Now this is the first instruction. This is an R format instruction because it has, usually they have three operands. There are some exceptions for this rule, three operands that are registers. As I was saying, there are some exception. I'm going to play it except SLL, which is shift left logical. It takes a value and it's R format, but we will discuss this later. So now this is the first instruction. I'm going to go into the second instruction of how come 10, 12, 13 were inside the register file. So I'm going to introduce another instruction called AddI, which is called AddImmediate. By immediate I mean a constant. So AddI, it has $RT, $RS, and then an immediate, IMM, I'm going to call it. So what this instruction does, it has register F, register file of RT is equal register file of RS, and we add the immediate or the constant. So the first thing we notice is that there is no longer an RD. So this is a characteristic of immediate or I format instruction. So AddI is actually an I format instruction. So in an I format instruction, we don't have RD, it's replaced by RT. So RT is now acting as a destination. So you can ask, how can we do this? It's actually very simple. As I told you, we have RS, the first source, RT, the second source, and we have RD, which is the destination or the address. What we can do is just add a multiplexer, and in this case we can choose between RT and RD if it's I or R. I format or R format will choose the destination of the place where we want to save our data. So let's go to the example where I want to place 10, 12, and 13 in T0, T1, and T2, and then add T2 to T3 and save in T0. So this is very simple. We use the AddI instruction to bring data inside the register file. So the way to do it is we do AddI, which we're going to start with T0. So we need to place 10. So the only way to place 10 is by actually adding it to 0. And we have this nice register $0, which is always 0, which comes in handy here. And now we can add 10 to 0 and place it in T0. We can have another instruction, T1 $0 12, add I, T2 13. Now I need to add them together. I can use the R format instruction add. Of course, this is the destination, the first operand, and the second operand. So here I'm adding T2 to T1 and save it in T0. Here we have T0 is equal to 25. So this is an I format instruction. Now, to differentiate between these instructions, we need to go deeper in what's an I format instruction, what's an R format instruction, what's the differentiation in terms of the components they are divided into. So we're going to start with the R format instruction. So with R format, we have something like this. So this is a 32-bit instruction. It has an opcode. We have RS, RT, RD. There's another component called champed, and the function. So with the opcode, it's just it is a component that tells us what is the instruction. So opcode indicates which instruction. So the MIPS library has many instructions, and the processor needs to differentiate between two different instructions. So the opcode is where this is used. We have RS, which is the address of operand 1. We have RT, which is the address of operand 2. RD is the address for the destination. Shamped is used for shifting. It's called shift amount. And function indicates the operation. So this is 6 bits, 5, 5, 5, another 5 also for shifting, and 6 bits. So here we have 32, a total of 32 bits. Now so RS, RT, RD, we saw them before. Shift amount, we'll see them in shifting operation. But what about the function and the opcode? So for an add instruction, it has a opcode and function of 0 and the function that is used is 22 hex. This is the value of the function. So all R format instruction has an opcode of 0. So all R format instructions have a value of 0. Actually they are 6 bits, so it's 60. Okay, so the way they differentiate between different instruction is through the function. So if we have an AND instruction, it will also have an opcode of 0, and the function will be 24 hex. For example, another R format instruction is sub. It has an opcode of 0, and it will have a function of 20. Well, actually I made a mistake. This is 20 hex. This would be 22 hex. So how can we, so why is there a function? We can think of a function as a controller for the ALU. The ALU does many logical and arithmetic operations, add, subtract, can do an and other things. So these are controlled by the function field. So the function tells us that what we're going to use is an addition or an AND or a subtraction operation. So what's the opcode used for then? It's used to tell the processor that we have an R format instruction and we're going to have 3 operands instead of 2 and a constant like in the I format. So now if we check what's the I format, the I format, it's like that. So this is the I format. So with the I format, I will have the instruction to have an opcode, to have RS, RT, and an immediate. So if this is 6 bits, since the opcode is fixed for all instructions, these are 5, since it's limited by the register file, we have a 16-bit immediate. So the immediate, or the constant in our case, is 16 bits. We have signed and unsigned, plus and minus numbers. So this gives us a range of plus 2 power 15 minus 1 and 2 power 15 minus 2 power 15. So this is the range of the immediate. We cannot have more than 2 power 15 values, or 32,000 and some 32,000 constant. So if you want 40,000 as a constant, we need to use other methods which we'll not go into. So this is the I format. We can see it has only 2 registers and an immediate. The immediate is 16 bits, which give us this range. There's also another form which is called the J format. With the J format, it has an opcode of 6 bits and 26 bits for this is the opcode, and this is the immediate, 26-bit immediate for jumps. We're gonna talk about this later. To finish up with an example, let's say we wanna write a MIPS assembly code for F is equal G plus H minus K plus I. So let's say F is important to me. I'm going to place it in a 0, and we can just place them in random registers that we know about. So here what we need to do is start with the parentheses, the operation inside the parentheses. So we need to add those two. We have add door. We need to use a register that I'm not using up there. You can use T4, T1. Now we need to add the other part. Now we need a subtract operation. Subtract is just like the add, it's an R format instruction. So since it's an R format instruction, we know how it works. We're gonna say this is the destination as 0, and we're gonna subtract T4 from T5. So this is a very simple problem that just does some simple operations. So in the next lecture, we're gonna talk about load and store, which are I format, which will deal with data memory.